Okay, so let's get started. So couple of notes. So now from lab 5 on, these will all be arena-based labs. And so you should have access to the lab textbook, the Kelton et al. Textbook. That, of course, I've provided online, so that should be pretty easy. There's also a hard copy that might be nice to have. Couple of notes is that this, as of December of last year, they updated from Arena 16.0 to 16.1. Sounds like a minor update, but although really nothing changed behind the scenes, well, there's a couple of minor things, but the biggest things that changed were right in front of you in the user interface. And so the user interface for Arena 16.1 will look quite a bit different than the user interface you'll see in the textbook and in some of the lecture notes. All of the same stuff is there, it's just a little harder to find. We'll learn early in our arena labs how to enable template panels, how to add template panels, and the old template panels for 16.0 and below, you can actually load, and then things look pretty much like they used to. But you're also free to use the new template panels, but you're gonna have to, when you look for the create block, which creates entities, it's in a slightly different location than it would be in the old one. So it'll take a little bit of looking if you want to use the new ones. Otherwise, you can load all the old template panels. The other thing is, if you decide to install Arena yourself on your own machines, before there's this thing called Crystal Reports Engine, which after you run a simulation, it generates a bunch of statistics for you and then displays them for you in a document. And the Crystal Reports Engine is what helps you navigate through that document. That, I assume for probably licensing reasons, although it was previously installed automatically when you installed Arena, now they distribute the installer with Arena, but they don't automatically run it. So I've put instructions on Canvas, if you're installing Arena yourself, how to go in and make sure after you're done installing Arena, to go through and install Crystal Reports Engine manually so that you get those report features out of Arena, which we'll refer to quite a bit. So those are some notes about Arena moving forward. A little bit of a speed bump, this update from 16.0 to 16.1. And it's actually a nice update. It's compared to the old user interface, it really modernizes it, makes Arena look. Arena is a program that a lot of people use still in industry, but it was looking very dated. This really makes it look like something that's, well, it still looks dated, but it looks dated by like 5 years, not 15. So it's a big update from Rockwell Automation. So props to them for doing that. It's a little frustrating that they kind of did it out of the blue and made kind of so many changes with no really great attempt for migration between the two. So, and also, of course, for those of us who teach with Arena, all of the teaching support that's out there is based on the old Arena. So it didn't give us a lot of time to make those changes. All right, so that's Arena moving forward. Homework, so the homework C, whatever the number is due tonight. Homework D2 has been available. It is technically due a week from today, but what I've done is made no late policy on it. So the normal 4 days after, where normally if you submitted it and during those 4 days, it would just knock down 20% per day. I made it so that there's no late policy for those days. So just to be kind of true to the syllabus, I still make it due in a week from now, but in reality, it's due like a week and 4 days from now. So you can use the availability date as the effective due date. So I did that so that immediately when it disappears, the availability goes away, date goes away, the solution sets will appear. So there's no waiting period between the due date and the solution sets. And then that way you'll have access to the solution sets for homework D2 before the midterm, because the midterm is coming up. To prep for the midterm, there's this ICAF, which is a midterm review. So after ICA E1 is due, so this is lecture D2, so E1 I think is the next lecture. So later this week, basically, F will pop up, and F is an ICA which is much longer than the normal ICAs, but you can take it as many times as you want, and it just samples random questions from all the other previous ICAs as meant to be kind of a midterm review. And so if you decide to take it and you do well on it, it's actually worth like 3.5 times more points than a normal ICA. So if you do well on it, it like buffers a lot of your score. So already we only have 12 ICAs, you get to drop 7. So really only 5 ICAs are counted. And if you take this one, then, and you do well on this one, and you can take this one as many times as you want, it can buffer against those ICAs. So it's a lot of flexibility there, and hopefully it generates questions for lecture F, which will be coming up, which is the midterm review lecture. So that's all I'm saying here. Midterms coming up. We finalized the dates there. So I forget it's 5th or 7th or 7th and 9th, but there was 2/3 of the class that voted, wanted the earlier stage 2. So we're going to have stage 1 will be on a Tuesday, stage 2 will be on the Thursday of that week. What I've done to add flexibility though is, although stage 1 will be available starting Tuesday, I will make the availability window go all through Wednesday. So you have 90 minutes to complete stage 1, but you can do it anytime Tuesday or anytime Wednesday of that week. It'll disappear Wednesday at 11:59 p.m. And then at midnight, Thursday, stage 2 becomes available. That's the collaborative part. And likewise, you'll have 48 hours there. So all of Thursday and all of Friday, you'll be able to do stage 2, but that's collaborative and it's not timed. So through that 48-hour period, you can chat with your friends. You can say, well, hey, what did you guys get on number 6? I didn't really understand that one, and so on and so forth, and update your answers as you wish. And then finally, you can either formally submit, or when the clock ticks down Friday at 11:59, then it'll get submitted. Stage 1's 80% of your score, stage 2 is 20% of your score, but the exams are identical between the two of them. I've put the midterm from last year, as well as the solution set, at least in PDF form, both of those, an empty midterm as well as the solution set online, as well as I think all of this, the midterms and solution sets back for, I don't know, last like 6 years or something like that. So there's a lot of those available, but the one from last year is probably the most similar than this year. I think the one from last year was like 37 points. One from this year is like 38 points. One from last year might've been, I don't know, 29 questions. One from this year is like 30 questions. So they're really similar. So they're similar in form and length and things like that. So if you want an idea about those two, I'll give those available. And this morning I was thinking about it, and I might actually just import the Canvas-based midterm from last year, because last year was still COVID, as a practice midterm for this year, so that you can actually, if you want, take last year's midterm on Canvas, of course, without respondents or whatever, just to see how well you do in that format. So I'll see about doing that. It shouldn't be hard to pull in from the previous semester. All right, so any questions about the midterm? I'm also staring online here. I see a question here online. Is stage 2 using lockdown also? Stage 2 doesn't use lockdown, it's just stage 1. And so about the lockdown thing as well, there is it's called like midterm compliance test, like tiny little assignment that also uses lockdown, that's due pretty much up until stage 1 midterm starts. Do that. That basically is just like a one question, like, did you see this question? Yes or no? Yes, type of quiz. But it confirms to me that all the technology is working on your system. So if you do that one, once you do that thing, it will unlock the midterm module. And the midterm module not only has the midterms in it, the stage 1 and the stage 2, but it also has all of these resources I'm talking about, the solution sets and so on. So take that compliance test to make sure that everybody's got the Respondus working. And you only will use Respondus for stage 1. For stage 2, it's open book, it's open notes, it's open collaboration. I ask you as an honor system that to only collaborate with people in the class. That's kind of the formal requirement, and to only use your own notes, the official textbooks, and the official notes from the Canvas webpage. So things that I've provided you or things that you've taken down yourself. You're not supposed to go and upload questions to websites, that's academic misconduct, or look for other information on websites, that's academic misconduct. But you're free to use stuff that I provide you, stuff that's on Canvas, and your own notes, and you're free to talk to anyone else who's currently enrolled in this semester's class. All right, let me see if there's any more online. Okay, any questions here about the timing or anything like that? And then, so if anyone's keeping track of the relative timing of this happens the week before fall break. Then you've got fall break, so that's like technically Saturday, Sunday, Monday, Tuesday. And then that tiny little week that's after fall break, we're just going to have a normal lecture on Thursday, lecture G1. That will be recorded, that lecture. That will be available to connect live. And you're also happy to come here. Plus you get, 5 or 6, depending on if you took that survey, drop lecture attendances. So depending on your travel plans for fall break, it's flexible and it doesn't hurt my feelings if you don't show up for that Thursday. So just letting you know, but that's all that's planned for then that Thursday of fall break. There is that Thursday of fall break. So lab 7 will be technically released during the midterm week, but I'm going to give you 2 weeks to do lab 7. So you don't really have to worry about lab 7 the midterm week if you don't want it. It's really a 1 week long lab. You can wait until the fall break week to do lab 7, or you can get it out of the way and then you've got no lab during the fall break. So tried to provide flexibility there too. Any other questions about scheduling a midterm or anything like that? I'm checking online as well. Okay. Yeah. Yes, if you go to the unit F2, which is the midterm unit, yeah, then you should find them all listed under there. Do you see them there? Do you? Great. All right. Any other questions? Yeah. Great question. So for stage 1, I give you, I say you can have 2 double-sided sheets that I call formula sheets. You can put whatever you want on them, as long as they're not like photocopies from other materials. So as long as it's hand produced, so if you want to type it, that's fine. If you want to hand write it, that's fine too. But it can be, it doesn't have to be formulas. It could be, I really had trouble with this question on homework D2. I'm going to copy that one down so I have that as kind of a reference. Or I need these definitions. Like I really have a hard time understanding the difference between entity and delay, but once I read the definition, I got it, that's fine. So whatever you want on them is fine, just as long as they're not photocopies. I really want you to go through the cognitive exercise of reproducing the material, either by typing or writing it out. Any other questions? All right, great. So just, again, the reminder here, if you're interested in the arena competition from Rockwell and IISc, I think the deadline is September 30th. There's, I think the FlexSim deadline for entry passed. I think it was yesterday, but if there are other simulation competitions, as long as they're discrete event system simulation competitions that you'd like to consider, I'm happy to consider those for your final project, just let me know. But keep in mind that most of them have entry deadlines that are sometime this month. All right, so I think we covered most of the questions there, but if anything comes up, of course, you don't have to wait for my question slides to ask me questions. Nothing online. All right. Okay, so where are we in our context here? We are now drilling down farther and farther into randomness and how we use randomness in simulation modeling. The motivation here is that we are trying to build simulation models that generate realistic variation. They are not, so you probably can't see it, but on this whiteboard, there's an ODE model of a relatively simple system from whatever the last class was here. It's a deterministic, if you were to integrate this ODE model, you'd get some trajectories over time, and those trajectories will be the same trajectories no matter when you integrated this. You integrate this now, you integrate this in 2 years, it's going to be the exact same trajectory. And that gives us, that's great for modeling trends of real systems, like what's the average behavior. But we want to actually generate realistic variation that we can do operations research on. We can do the quality control analysis. We can try to do, like, you could do 6 Sigma on a simulation, like you can study, how many broken widgets do I get out of this simulation, and what strategies can I do to squeeze that distribution down so that I can meet my 6 Sigma, threshold, and so on and so forth. To get that realistic variation, we need to somehow put something that's variable into our simulation model. And we do that by the stochastic approach. And the stochastic approach is a philosophical approach to modeling where we introduce randomness in the model, even if randomness may not occur in the real world. And that means that we can basically gloss over the details of why variation happens in the real world and instead replace it with a dice roll. And as long as we weight the dice just right, then hopefully we can shape the outcomes of that dice roll to look realistic. There might be good deterministic reasons why the real world produces the variation it does, but we would have to account for millions of factors in order to understand the deterministic relationship between what's going on in the environment and what happens at every instant of time. We don't want to worry about that, especially if we can approximate it with randomness, and that's what we do in stochastic modeling. So input modeling is the process of choosing the right probabilistic models, of weighting that die roll or that dice, so that when you roll it, it comes up with outcomes which look realistic. You know, if you're playing a board game, you probably don't beat the dragon 9 times out of 10. It probably beats you 9 times out of 10. So you need to make sure that you choose the schedule of who wins, so that the die roll comes up so that you win a realistic fraction of time. Now, if you do that right, then if you were to fight the real dragon in the real world, you probably would win, you know, 1 time out of 10. And likewise, if you roll that die roll, it comes up as a win 1 time out of 10. So it ends up matching, even if we glossed over all the details of exactly how you beat the dragon. That's what we're doing here. So in order for us to introduce randomness, we have to understand how to model randomness. In order for us to introduce random models, probabilistic models, those are our inputs, our simulations. Probabilistic models of activities are example inputs to our systems. We need to understand probability a little bit more. And so we talked about the probability space last time. There's a sample space, which are all the mutually exclusive outcomes that can happen in an experiment. We talked about a random variable maps that sample space to the real line. We talked about how any set of those outcomes is called an event. And we talked about how the probability measure weighs the event to give it probability. So all of the properties of probability are similar to the properties of mass. And so if the probability of 2 outcomes is X, the probability of outcome X, or outcome 1 plus outcome 2, if you add those together, it should also be X. The same way, if the table weighs so much, if I break it into 2 and then weigh the constituent parts, if I add those up together, it should be the same as the table. That's how the probability works here. So probabilities of any event will always be greater than 0. Probabilities of the whole sample space will always be 1. And any subset of the sample space, any other event, will be in between 0 and 1. And so that says the random variable is this function which basically allows us to stop talking about outcomes and start talking about numbers. And so the random variable gives us this power of generalization where we can say that's a Bernoulli random variable. Well, a Bernoulli random variable is representing the only outcomes of a Bernoulli random variable are 0 and 1. Well, we need a mapping to say what the heck's 0 and what the heck's 1. That's what the random variable does. So the random variable takes outcomes from the real world and maps them to numbers like 0 and 1 so that we can define things like Bernoulli random variables, normal random variables, things that we can talk about very abstractly and generally, which represent a wide range of systems. And so we said, based on that random variable, that there are different categories of random variables that relate to their ranges. And so if the range of a random variable is countable or finite, we call it a discrete random variable. And we refer to the probability of any outcome as having mass. So every outcome has mass. And if we collect all of the outcomes together, we get a probability mass function, which we can sort of show in this distribution here, where these are our 6 outcomes, and these are the probability masses of each outcome, where I use this little pinhead thing, which is called a delta measure, to say that there is so much mass concentrated on that point. This really can be thought of as a sort of a seesaw or a teeter-totter, and each one of these might be children that are sitting along that seesaw, and maybe these are younger children that are lighter, these are older children that are heavier, and so if we were to guess where the fulcrum needs to be in order for this seesaw to be balanced, that guess, which is probably say over here, actually is going to be the mean of this distribution. So you should be able to look at a probability mass function or probability density function and guess where the mean is, because it would be that if you were to build the thing and balance it, it would be the point that it would balance. All right, so that's discrete. Continuous is a similar story. but instead of concentrating all the things like 6 children sitting on a wire, then instead we think about like a table that has a higher density at one end and a lower density at the other end. If you weigh any sliver of the table, it's 0 weight. So the probability of any outcome is 0 everywhere. But if you weigh an interval of the table, then that interval has weight. And so we have to integrate under the density in order to get the weight. Density is not probability. And so density can be greater than 1, but the integral underneath density should always be 1. If you go all the way from negative infinity to infinity. So that's our continuous random variable. And that's all I'm summarizing there. So this is an example of where densities can be greater than 1. Here's a uniformly distributed random variable between 0 and 0.5. In order for the area underneath the density to be equal to 1, the density from 0 to 0.5 has to be 2. So f of x, the density of this random variable, is greater than 1 because 2 times 0.5 is equal to 1. Likewise, for an exponential here, this is an exponential with a mean of 0.1. So if I were to try to balance a shape like this that had a bunch of mass that or a bunch of density from this point here to the left, then my fulcrum would probably be around 0.1 because I've got this long tail, which has got a big lever, which is sort of holding up this mass. And this mass does not have a big lever, but it's very massive. And so we'd end up getting that fulcrum being around 0.1. That's where the mean is there. The area underneath this exponential curve is equal to 1. But for this particular curve, that means that the density at 0 is equal to 10. So densities don't have to go, don't have to be bounded above by anything. Densities can just go and go and go, just so long as the area underneath them is equal to 1. It's the same thing with, I mentioned, if I have a tabletop, I could have density equal to the density of the sun. It's just the edge of the table. And that number would be gigantic, but the mass of the whole table might be far less than that number. And so they're just different units. So it's unfortunate that when they came up with probability density, they didn't like to me as an engineer, I wouldn't say it has a density of 1. I would say it has a density of 1 per meter or something like that, or 1 per square meter. I would make it clear that there are different units to probability and probability density. But mathematicians don't think in terms of physical world, and so they just drop the units, and then we're stuck with density and probability both looking unitless. When in reality, density is not units. Okay. So any questions about these distinctions, about mass and density when we talk about probability, about the fact that probability density, when you look at these distributions, can go way higher than 1, even though probability mass is always going to be bounded at 1. That makes sense? Hopefully review. Nothing online. Okay. All right, then we talked about moments. I already kind of gave our cumulative distribution function. So if we'll very often not use density or PDFs or PMFs in this class, we focus a lot on CDFs, cumulative distribution functions. They're extremely useful things. Big F of x, for regardless of continuous or discrete, is just the probability that the random variable is less than or equal to whatever the little x is in the argument. And so that, for a discrete random variable, you just sum up all the probabilities of all the outcomes less than that in that outcome that is in the argument. For continuous random variables, you just take the integral from negative infinity all the way up to the argument. And that is sort of like taking a sum where you've got a density f of t times a tiny little width of the sliver. And so this together, f of t dt, is effectively a probability mass of a tiny, tiny little sliver that's slightly non-zero. You can kind of think of it that way. So these are effectively the same definitions. And then that just accumulates these densities or these probabilities as we go from left to right. And because you're accumulating, it's monotonic. So if you go from, if A is less than B, then f of A will be less than f of B, or less than or equal to. The limit of this thing is always equal to 1 because probabilities are bounded above by 1. The limit of this thing on the other side, negative infinity, is always 0 because probabilities can't be any lower than 0. And if I ask you for the probability on an interval here of, that x is between a and b, I can just say, well, that's f of b minus f of a. I don't have to do the integral all over again because it's effectively been done for me. So CDFs have a lot of power. They simplify a lot of things, and they're going to allow us to do some pretty cool things as we move on into lectures or units D and E. All right, so questions about CDFs? It's pretty clear. Again, hopefully review. I don't want to belabor this too much if this is old news. Okay. Questions online? All right. All right, so I said we can do cool things with CDFs. So here's an example. So I talked about when we were looking at Excel-based models of discrete event system simulations, an input model you might get is of these service times. So you could say that you go up to a cashier and 30% of the time, it takes 3 minutes to get through that cashier. 45% of the time, it takes 6 minutes, and 25% of the time, it takes 10 minutes. Maybe cashier was a bad model here. These seem like they'd be really long for that. Or maybe these are seconds or something like that. Maybe this is seconds going through a gate checker at the airport. So 30% of the time, it takes 3 seconds to get through there. 45% takes 6 seconds, 25% takes 10 seconds. So that is our probability mass function for these 3 discrete outcomes. So, and I used minutes down here. So this cumulative thing over here, this I can view as another way of stating these things. But I say instead, it will take 3 minutes or less with 30% probability, 6 minutes or less with 75% probability, 10 minutes or less with 100% probability. And if you notice that for this first entry, it just copies that probability mass over. This 0.75 just comes from taking the 0.3 from the previous one plus the 0.45. And this 1 just comes from taking the 0.75 plus the 0.25. So this CDF is just a restatement of the PMF, but just in a slightly different terms where I've accumulated the probabilities as I go. Now, if I plot that, so that I've got outcomes on the x-axis down here, 3, 6, and 10, and the CDF on the y-axis here, 30%, 75%, and 100%, then I can do something useful when it comes to simulation. And that is, I can do what's called the inverse transform technique, where if I draw a uniformly distributed random number between 0 and 1, which we're going to learn how to do, then I can use the inverse of the CDF. So taking this graph and using the y as the input and the x as the output, then I can then draw these 3 outcomes in such a way that will be consistent with my desired probability density or mass function. So if I draw any number between 0.3 and 0.75, that will map to a 6. If I draw any number between 0.75 and 1, that will map to a 10. If I draw any number between 0 and 0.3, that will map to a 3. And sometimes this is referred to as the random dart transformation, where if I were to kind of unroll 0 to 1 and create intervals of length equal to the probability masses that I desire for each outcome, I sort of reproduce the cumulative distribution function. And if I were to throw a dart randomly on this from 0 to 1, then the length of these intervals is what gives me the desired probabilities of each outcome out. So because this interval is longest, then this outcome 6 happens most frequently. Question? So I think the question here was about, like, if I draw a number between 0 and 1, what the inverse transform technique is doing is it's seeing that what we're gonna, and I'll write when we get to this, we'll write it out formally, so it's not just graphical. I think the issue is that I'm trying to depict it graphically here, but it's saying here that any number greater than 0.3, but up to and including 0.75, we're going to map it to here. So there's going to be an interval where if you happen to fall in the interval, that so this outcome, you choose an outcome if the drawn probability is equal to or less than that outcome CDF, but greater than the previous outcome CDF. Does that make sense? Other questions about that? It's kind of random dart transformation. We'll talk more in detail about this, but I'm just using this to motivate one of the ways in which we make use of CDFs inside our simulation models. Because if we can specify an input model in terms of its CDF, we just need to be able to write the CDF in a way that the computer can understand it symbolically. And then the computer can generate whatever random distribution we want. This is the way we write the cards for the board game. So the board game says, when you roll a 20-sided die from 0 to 15, it's this outcome, 16 is this outcome, 17 to 20 is this other outcome. That's what we're doing here. And so how do we specify the little cards for the board game that we can give to the computer when the computer is implementing the board game? We do it by giving the CDF of our input model. And we can do this with a continuous as well. So if I have a CDF for an exponential like this, there may not be a function inside Excel or Arena. There is an Arena to generate an exponential. But there is the ability to generate a uniformly distributed random number between 0 and 1. Then what do? How do I generate an exponential? Well, I solve for the CDF of an exponential. That's this nice little function here. If I set that thing equal to some, r, and then I invert it so that I solve for x in terms of r, then that will end up allowing me to basically do what I'm doing here in this graphical thing, where I'm taking the y-axis as an input, the x-axis as an output. And then if I draw any number between 0 and 1, this little transformation, pushing things in from the left and bringing them down out from the bottom, then that stretches out a finite interval from 0 to 1, so that's a finite length interval, to an infinite interval. So as the numbers get closer and closer to 1, the outputs will get farther and farther away, all the way up to infinity. And so that is what is going to allow us to get that heavy-tailed distribution of the exponential through this transformation here. So the CDF is what can allow us to turn a randomness that's easy to generate, uniform randomness between 0 and 1, just like a uniform die roll between 0 and 20. It's easy to generate that. Just have a fairly weighted die, and it's easy to get numbers from 0 to 20. Imagine a 100-sided die, a 1,000-sided die. That's like generating a random number between 0 and 1. And then you just create this kind of table, this lookup table that maps those uniform outcomes to these non-uniform outcomes. And that's what we'll be doing in Unit E. So this is me kind of showing that these regularly spaced intervals are irregularly spaced over here, and that's by nature of this inverse transfer. Okay, so questions about that? Is that clear? I mean, it doesn't have to be super clear. We're going to get to it. This is all Unit E. And I'm just trying to motivate why we really care about the CDF in this class, because we're going to use it as a way to communicate input models to the computer. Okay, questions online? Doesn't look like it. Great. All right, and then moments. Already kind of summarized all of this. The biggest thing we really worry about in this class is mean. So I'm not going to spend too much time on this, but I did mention that if I show you a probability density function or probability mass function, you should be able to use your intuition from living in the physical world to guess where the mean is. And that mean is the balance point of that distribution. So I look at this distribution, and if I were to put a little fulcrum under there and say, at what point does it perfectly balance, then that would be the mean. So, so that's why when we talk about distributions that have skew, that usually means that their mean has been moved away from their median or their mode. And that's and you can kind of think of that as weight has been added far out here that causes things to tip a little bit. And in order for us to correct for that tipping, we have to move the mean over. So the mean is constantly balancing out all the extra outliers over here. This is, when we talk about means are very sensitive to outliers where medians aren't. Well, you can think of that in terms of mass here, is that the fulcrum here, because of leverage, if you put just a little bit of outcomes way the heck over here on the far right, for those who are not in the class right now, then in that case, due to the leverage effect, then this would very easily tip this thing. And so we have to move the mean over. So means are very sensitive to outliers. It's another way of saying that with an infinite lever, even a P can cause something like this to tip. Same thing with discrete. If I give you a bunch of discrete weights, just pretend like there's nothing in between them, and you can guess roughly where, if I were to sit them on like a teeter-totter, where would the middle of the teeter-totter have to be in order to balance this thing out. That's where you can guess where the means are. And if I were to happen to sit someone right on top of the fulcrum of the middle of this thing where it balances, it doesn't affect things. Similarly, if you add an outcome in a distribution which is right at the mean of that distribution, it does not change the mean of that distribution. So, if you could say that we went from 6 outcomes to 7 outcomes, but the 7th outcome is exactly the mean from the 6th outcome, it doesn't actually change the mean of that new distribution. The same way, sitting someone in the middle of the teeter-totter doesn't cause it to tip. And then those higher moments and variance. The big thing we worry about in this class is this formula here, that variance is the second moment minus the square of the first, and that standard deviation is the square root of the variance. Kind of the big points there. So these things down here, and we will use sigma for standard deviation very often, and sigma squared for variance very often, just like we'll use mu for mean very often. All right, so questions about any of that formality stuff, definitions and so on. Feel good about all of that. So those are terms that we'll use when describing a bunch of models. And so today we talk about how do we pick models for different processes. Okay, well, let's do a quick concept review here. I could turn this into an attendance question. We might, but maybe the next one I will. So let's look at this. And as a show of hands and as entries in the chat, which one of these is the cumulative distribution function? So how many people think, so in the chat, put either A, B, or C, based on which one of these you think is a cumulative distribution function. In class, how many people think this is the cumulative distribution function? All right, we got 1 or 2. How many people think this is a cumulative distribution function? We got a few more, say 6 or 7. How many people think this is the cumulative distribution function? We've got, say, 2 or so. Okay, let me see online. I've got a bunch of B's online and an A. So what do we know about cumulative distribution functions? Can somebody give me a fact about cumulative distribution functions? You can also give me a fact in the chat if you like. So remember, in the cumulative distribution, the area under what has to equal 1? Is it the cumulative or is it a different one? Under the density function. The cumulative distribution function, the area under the cumulative distribution function doesn't have to equal 1. The area under the density function has to equal 1. So that's the PDF versus the cumulative distribution function. In the back there? Non-decreasing, that's one of the things there. So non-decreasing. And I've got another fact out here, and at infinity, it's equal to 1. So, those are 2 things that are useful here. Maybe in Zoom, I can flip on the annotation tool here. There it is. And draw. All right, so apologies for the handwriting, which I'm sure will be terrible here. So we know that non-decreasing, so this is me trying to write non-decreasing. And we also know that from the chat, we've got here that F infinity is equal to 1. All right, so those are properties of cumulative distribution functions, not density function or mass functions. So when I look at this, I think, well, this is decreasing, so can't be that. This one is increasing, so maybe it's a CDF, but at 1, it's already up to 100. And I know a CDF can't be any higher than 1. And I know at infinity, it's equal to 1. So that tells me that down here, that B, that must be the CDF. So if I go over here, B must be the CDF. And so if I look here, B is equal to, at 0, it's equal to 0. At 100, it's approaching 1. It never quite gets there. And it's always rising. And this is actually the CDF of an exponential right there. Okay, questions about that? Look online. All right, so with that in mind, let's say we wanted to find that density function. So how many people think that A is the density function? And online, you can vote. Which one do you think is the density function, A or C? You can just put your letter in the chat. So we said we got sort of 1 there. How many people think C is the density function? About 1. Seems like there's a lot of unsure. We're not quite sure here, and that's fine. So what do we know about density functions? There's already mentioned that area underneath them has to be equal to 1. So for density functions, and then online, it looks like I don't have any votes online, so nobody likes this exercise. So so if I clear, so what do we know? We know the area for a density function, area under, I'm just going to say AR is equal to 1. And so it's hard to tell the area underneath things. I know for B, the area underneath this is probably not equal to 1 because it's got 100 on this axis and 1 on this axis, and it's most of the plot. So this little bit here, like this giant part here, is probably close to 100 times 1, which is 100. So it's probably not an area underneath 1 here. So that's probably not the right one there. But these, I can't really tell if the area underneath here is 1 or the area underneath here is 1. They might both have an area equal to 1. But if I look at them, so this is one of these things where really there is no way for me to tell the difference in terms of density between this one and this one without specifically knowing if this thing's area is equal to 1, because I know that density functions can go up to 100. They're not bounded above. And I know that they don't have to be defined over the whole, I mean, they have to be defined, but they don't have to be non-zero for the whole real line. So there is kind of a big question mark as to which one of these is a density function. Now I can tell you that this one is the density function. This is a density function for an exponential. I know that because I generated it. And I can tell you that this thing over here is what's known as a quantile function. So I'll write quantile, or try to write quantile with my finger, otherwise known as the inverse CDF. So I could also call this the inverse CDF. And so if this is a CDF, I can take a diagonal line across it, and I can fold it along the diagonal line, and that operation gives me that. So notice this goes from 0 to 100. If I fold it, then I end up getting this thing. So the 0 to 100, 0 to 1, then my 0 to 1 is on the x-axis, 0 to 100 is on the y-axis. And so this here is our inverse CDF, which is the thing that helps us map a random outcome from 0 to 1 to a random outcome from 0 to infinity. So this is the generator of an exponential given a uniformly distributed random number. So if I were to ask you which one's the density function, formally you can't really tell. You just know this one's not the density function. But I can tell you, because I generated these, this is the density function, this is the CDF, and this is its inverse. All right, so questions about that? Okay, showing you plots like these and asking you about them are great things I could do like on a midterm. for example. So being able to spot these things. I wouldn't ask you in this one, which one's the density function, because you couldn't actually tell. So it would be obvious, or it would be, there would be a clear way to discount everything else, whatever I'd ask you for. Questions online? All right, I saw some votes, and a couple people said A and a couple people said C when I asked for the density. But A was the density there. So let me clear these. All right. All right, so I could also ask you about these sorts of things. So now that we've had that little exercise, then if I just were to focus on these here, which one is the CDF? And so those who are in the chat, go ahead and give me letters. So D, E, F, or G. Otherwise, I'll do the same sort of voting thing. So those in class, how many people would say that D is a CDF? All right, see like 3 or 4. Okay, how many people say E is a CDF? Nobody? How many people say F is a CDF? Nobody? How many people say G is a CDF? All right, nobody. So of the little sample that we had here, I think we had a lot of no votes, but we had I think a large majority of the votes for D being the CDF. And if we think about what do we say that are, let me look online too. Online, we've got all Ds. So it seems like CDF, everybody is happy about D, and that's great because that's the one I would choose too. D is non-decreasing, it's always increasing. It starts at 0, it goes to 1. All the properties that we need for a CDF. Okay, now if I were to ask, what's the density function? What's a reason why E could not be a density function? Anybody have a guess? Yeah. Well, remember, densities can go above 1. So what? Yeah, in the back. It goes negative. That's right. So, and I got that online too. So a couple people said negative. E goes negative. Densities can't be negative. So E cannot be a density. All right. So what's wrong with G? Like in general, like could G be anything? G is not even a function, right? So G is what I would call an inverse density function. And that kind of gives away what the density function is here. It's when you take F and invert it. But F is not invertible. So G, if you were to ask, well, what's the value at 0.5? Well, it comes out to either negative 0.5 or around 0.5 or something like that. So because there's 2 answers for one question, it's not even a function. So G is, there's no such thing as an inverse density function, but F is the density. So if I were to integrate under F, I would get D. So F is my density here. And the big things about F is it's always positive. It can go greater than 1, and the area underneath it happens to be equal to 1. I can't really evaluate that visually. I can tell you the area of the whole square is 4 times 1.5, which is like 6. And then I could say, this might be a 1/6 of the square, but it's really hard for me to evaluate that visually without maybe, cutting up little rectangles, Riemann-like, or rectangles the other way, Lebesgue-like or something, and then adding them all up to 1. But I can't really tell. But I know that everything else can't be a density function. This has got too much area underneath it. This one's negative. This one's not even a function. So that's our density. All right. And great. And we got some people online said the same thing. G, not a function, multiple Y's for a single X. We got that. Good. All right. So any questions about that exercise? Graphically evaluating what's what. I could also ask you to sort of say, like, roughly where would the mean be for F? And you might say, well, if the peak is here, but because there's all of this stuff over here, the mean is probably on the right side of 0. I don't know if I'd ask something like that. That's a little ambiguous. But if I did ask something like that, I'd make it more clear. You can imagine if I built this thing and I tried to balance it, where would it balance on? That's the mean. Okay. And I want you to spot these things because your stakeholders will often give you data distributions and things like that. And I want you to be able to spot plausible distributions. And then also, if somebody proposes a distribution, like, oh, we used a normal distribution with a mean of whatever, you know, when you look at a histogram, I want you to sort of, even if you can't evaluate if the distribution's right, I want you to be able to spot, like, well, you know, that mean can't be right. Because if you just look at that thing, there's no way the mean is over there. That's what, like, engineers are big, like, back of the envelope type of people, you know, and that's why you want to get that back of the envelope intuition. And so being able to do this stuff visually is really helpful. All right, so any questions about this stuff before we do a quick tour of some of the common probabilistic models that we'll use in the class? And I'll probably skip some of this summary stuff. Okay. All right, so let's do an attendance question just to give people credit for hanging on so far here. So I'll put the link in the chat. And the question I'll give here is, what is one property of a probability density function, PDF? Just list a property. You can, if you like, you can use f of x in your answer. Like, you don't have to write a whole sentence. You can just say, you know, f of x squared is equal to 5 or something like that. That's fine. So that's not a property. Don't do that one, but do something like that. That would be fine. PDF, probability density function. And yeah, density function PDF. Okay. All right. Okay, so moving forward, talk about some common distributions. Lecture E1, how do we get those U01? How do we get the uniformly distributed random numbers, which is like homework C2. Lecture E2, how do we take the uniformly distributed random numbers and turn them into anything else? And that's like homework D2. Then lecture F is our midterm review, and then our midterm. So yeah, input modeling is how to select these probabilistic models. Probabilistic models, we want to make sure we get realistic probabilistic models, realistic input models. We push them into our process diagram, and we get out of it outputs, and that output will have variation, which we can then do stats on. Again, you can do your 6 sigma on these outputs. You can say, do I have most of my, you know, do I get 3 failures per million, or whatever the heck your stat that you're shooting for is, you can look at in these outputs here. But these outputs are only good as those inputs. And so, so we need to make sure we're choosing good inputs here, because we'll get variation for any inputs we choose, but we can only trust the output variation if we trust the input variation. So what are our options for those input variation? Well, these are some common ones. So in your career, you will become familiar with these as a foundation. We're not going to be familiar with all of these in this class. I'm just going to start you on a little hors d'oeuvre, I guess, a little appetizer of these, just to cover some of the bases. But these are the ones that I would recommend you become very familiar with as you move on into your careers. The ones we focus on in this class are the ones that are left kind of dark here. So like uniform, triangular, normal, exponential, Erlang, and Weibull. And the other ones will get filled in as you start doing more of this stuff in your career. On the discrete side, Poisson, Bernoulli, binomial, negative binomial, geometric. In some of these you may have seen in 380 or 385. Some of them you will see in 470. You know, where do these basic ones come from that I'm highlighting here? So like uniform distribution, we've been talking a lot about already. This is the, and all of these, I'm going to have the density function on the left, the cumulative distribution function on the right, or in the case of discrete, I'll do the PMFs here and the CDFs over here. And then likewise, the formulas for the two of them over here as well. Basically, a uniform random variable is a random variable who only has mass or only has density on an interval, and it's a constant density. And so there, you can think of this as having an equal likelihood of anything happening between A and B. This is a good choice of input model when the thing that you're trying to model, the only information you've been given ahead of time is that it has a lower bound and an upper bound. So if you're given a data set, maybe you might fit this to a data set, but you often use this when you're not given a data set. Somebody just tells you ahead of time, I don't have the data for that just yet, but I can tell you this service time never goes below 2 minutes, never, ever. In fact, we have a a process control that prevents it ever from getting less than 2 minutes, and we can trust that, but it will also never go higher than 10 minutes. And that's, it's always going to be between 2 and 10, and it's just like, there's no real trend in between there. In that case, because okay, I'll use a uniform for that. And these are sort of the properties. The mean of a uniform is right in the middle of the uniform. There's some other properties about its variance. I've given you just sort of stuff about its CDF here. This is all just kind of formalities. The big thing that we really like about the uniform in this class is that it is easy to generate a uniform with a deterministic computer. We'll talk about how to do that in lecture E1. And once we have the uniform out of this computer, then a link typed in. Oh, sorry about that. So let me retype that link for the people in the chat. I flipped the the 2 numbers and the link, the attendance link. All right, so once we have the uniform distribution, then we can generate any other distribution we want. And so one of those other distributions might be the triangular. Again, this is another one of these distributions that we can fit to data, but most often we use the triangular when someone tells us it will never be lower than A, it will never be higher than B. Most of the time it sits around C. So it's hard to get data sometimes without investing a lot of money and effort, which, some of that effort you'll do when you're doing your final project. You'll actually take data on people. But when you can't take that data, people's intuition might tell you where things tend. So things tend to this value here. And so the triangular distribution is for that. So it looks like this. That the density function, it's 0 until the lower bound, it's 0 after the upper bound, and it rises to a peak in the middle. The triangular distribution, don't really have a whole lot of other things to say about it. The uniform distribution, I can say mathematically, is the best distribution to choose when you only know these bounds. And by the best, there's something called maximal entropy. It maximizes the entropy subject to the constraints that you only have these bounds. And so any other distribution you would choose here that would fit between these bounds would reflect your personal human bias. This is the least unbiased distribution for when you're given 2 bounds. I can't say anything mathematically about the triangular distribution. It's just convenient when someone wants you to enforce a tendency. Now, another kind of distribution that has a peak like that is the one that you've seen a lot of, and that's the normal distribution. So when do we use the normal distributions? Well, it is a great choice when someone comes at you and says, this thing is practically unbounded. And what I mean by practically is it might be something that it doesn't make sense that it ever would be negative, but the mean is so high that negative numbers that would come out of a normal would happen so rarely that they could be neglected. You could forget that they even exist. And so something that's practically unbounded means that it is actually unbounded from negative infinity to infinity, or it's the hump of this bell curve is so far away from the problematic values that we can consider them never happening. And so if they say that it's basically unbounded and it has a mean and a variance, this mathematically is the best distribution to pick for that. So they tell you mean and variance, they don't tell you any bounds, that's a normal. Normals show up all the time in physical systems because of the central limit theorem. I'm walking around on carpet. Now notice as I walk around on carpet, I have an average tendency to walk in an L pattern. So back from the chair and then go over here. Now, every time I do that, I vary a little bit. There's going to be an instructor who comes into this class afterwards, and they might also walk in that. They're not going to walk like me, but there's probably an average tendency to walk in kind of an L pattern. If you took a cross section, say right here, of this carpet, and pulled up this carpet square and looked at a carpet pad underneath there, you would see a wear pattern. And that wear pattern would be very light here, and would be heavy right in the middle. And if you were to then plot the wear pattern on a, on a curve here with maybe distance from center, it would be a normal distribution. And that's because of the central limit theorem, because every time I walk around, there is some random variable that's not normal that describes where my next foot is going to go, exactly where it's going to go. But every time I walk through here, my next time I walk through here is independent of the previous time I walked through here. And so every time I step, I add to where that has been stepped on here before, and every addition is independent. So it's the sum of a bunch of independent random variables, which we know by the central limit theorem approximates a normal distribution over time. If you look at every door handle that you look at as you walk around going through the university, you'll find, if you look closely, it will also have wear patterns that will have a peak in the center and then fade out after that. And that's because of the central limit theorem. And so we use normal distributions all the time when we detect a possibility of additive wear. So anytime there's in a system, now this could also be when someone's assembling something at Subway or something like that, or at some restaurant or whatever, and it takes a certain amount of people a certain time to do some sequence of the, to cut the bread. And then it takes a certain amount of time to put the lettuce on, a certain amount of time to put the tomatoes on. The time it takes to put the tomatoes is independent of the time it takes to take the lettuce. The time it takes to put the lettuce on is independent of the time it takes to cut the bread. Now you add all these things up together, and if you were to model the entire process of making a sandwich, it tends to be normally distributed because of the central limit theorem. So additive processes, you should think, maybe I should start with a normal distribution if I don't have any other data. Additive processes, normal distribution. Does that make sense? Are there questions about that? Kind of build up intuition into why the heck you would choose a normal over a triangular, and normal, this additive thing. Okay, so bell curves, symmetric distributions, normals are symmetric. That's the other kind of big thing about them. Again, think central limit theorem, additive wear. The other big tool in our toolkit for this class will be the exponential distribution. You should think exponential if someone tells you non-negative and known mean. I can say mathematically maximal entropy. So there is a way for me to say this is the least unbiased distribution when someone tells me that a process is non-negative and has a known mean. It pisses me off so much when I see people being amazed when they take histogram, not in this, it doesn't piss me when students do this, not saying that. When colleagues, especially colleagues from other disciplines, show me a histogram of their data, and they'll very often see, they're expecting, I have colleagues that will expect that even though it's non-negative, they'll just expect that the null distribution, like if nothing exciting is happening, would be like a uniform distribution of values between A and B or something like that. And they'll show me like, oh, look, Ted, it's not uniform. It's like the golden ratio, the planets of the line. There's something exciting and going on here. If you see an exponential distribution in data, most of the time, this is the null. Most of the time, that just tells you that you're dealing with data that's non-negative, that has a consistent mean. If that's all you know, non-negative and zero mean, the least unbiased distribution you should pick is this one, the exponential distribution. So what's examples of those sorts of things? Like failure times, for example, waiting times. So how long do we wait for the next student to come in? Well, we know we can't wait a negative amount of time. We know that it might be instantaneous. We know that in theory, it could happen an infinite amount of time. So what's the best guess? Well, I know that on average, we get about 30 students per hour. So I'm going to do 1 divided by 30. And that exponential with 1 divided by 30 is my average. That is the distribution that I'm going to use for the time in between students arriving at the class. So that's what we use an exponential for. Non-negative values with a known mean. It's the least unbiased distribution to use. You're going to be tempted when you start your career to use normal distributions and things like that. Like, oh, they told me that on average, people arrive once every 5 minutes. So I'm just going to put a normal distribution there, and a standard deviation, I don't know, let's say a minute or something like that. But don't. If you weren't given a standard deviation, if all you're given is a mean, it's non-negative, this is your distribution, the exponential. Questions about that? All right, now, the exponential has this really cool property called memorylessness, or the memoryless property. So I mentioned that you guys will learn in 470 that for queuing networks, there's a thing called Kendall's notation, where you package into 3 letters or 2 letters and a number, the input models, basically. So you know that the inter-arrival times are a particular distribution that's encoded by a letter. The service times are a particular distribution encoded by a letter, and how many servers are particular, or the number. And M is the letter they use to encode the exponential. M can stand for Markovian. It also can stand for memoryless. The memoryless property is that the amount of time you've been waiting for something to happen does not give you any information about the amount of time left to wait. So if you're waiting on a bus, it's not memoryless, because you know that a bus arrives every 10 minutes. So if you have waited 7 minutes, you know the bus is probably going to arrive in no longer than the next 3 minutes. You don't know how long the bus had not been there before you arrived, but you know that as you get closer and closer to 10 minutes, there's higher and higher certainty the bus is going to arrive. That is not being memoryless. Being memoryless would be arriving at the bus, and the amount of time waiting for the bus doesn't give you any information about how much more time you have to wait for the bus. And that is the property that the exponential has, this memoryless property. And so there are a lot of systems that are approximated by this memoryless property. So again, failures or whatever, you know, when the waiting time light bulb fails, you know, if you say, okay, you reset the counter and you wait for the next light bulb to fail. And you say, okay, it's been 3 days and that light bulb hasn't failed. Well, now if a light bulb has a lifetime of 20 years, if it's like an LED light bulb, then the fact that you've waited 3 days doesn't give you any more information than when you've waited 3 years. It doesn't really tell you anything more about the short-term future. Now, in the long-term future, of course, reliability, that LED light bulb is going to die. But in the short term, we can approximate it being memoryless, and that's what this memoryless property is all about. Questions about that property? Super important property. And again, this is why if you're modeling a bus station, you would not use an exponential to model waiting times for a bus. Yeah. Good question. So, I mean, the question is, at what point do you put if you put an exponential into your model and the model outputs stop matching reality, then this can be the choice. Like you can say, well, it's a bad input model. Like you were modeling this transit system and you modeled the buses coming according to an exponential distribution. Well, we've looked at your buses. Some of your buses arrived after a minute of waiting. Some of your simulated buses took 1,000,000 years to arrive, because that could happen with an exponential. That is totally unrealistic. And because of that, then your service stats look totally, you know, they look much worse than reality because your buses, you know, have this funky distribution. So, so it kind of depends on the time scale of your analysis and the research question that you're asking. So if I'm analyzing how often do I need to worry about replacing light bulbs in the span of a classroom, occasionally I've had light bulbs burn out on me while I'm in class. And that's an interesting problem, but that I probably could model with a memoryless with an exponential. But if I want to think about the long-term planning of the life cycle analysis of the building or whatever, then I probably need a more realistic distribution for the failure times for these light bulbs, like a Weibull or something like that. That's right, absolutely. So sometimes you have to know that the statement was to know the problem or to be, it's really about the question. Is you have to ask yourself, again, all models are wrong, some are useful. And so at what point is it so wrong that it ceases to be useful? And so for some questions, you can be way wrong, but it doesn't really, but the question is insensitive to this choice. You just need to make some choice. Okay. Any other questions about this funny little property? Questions online? Okay. So now that we know the exponential, we build distributions on top of the exponential. The first one we build is the Erlang or Erlang-k distribution. We add another parameter to the distribution. And Erlang is what happens when you add exponentials up together, independent exponentials together. So I might have a light bulb, and then I might have another light bulb right behind it. And my question, it's, you know, so when that light bulb dies, I got this one ready that I'm going to swap in its place. And my question is, how long are those two light bulbs going to last me? Well, now I've got that failure time and this failure time added together. So an Erlang-k will give me the distribution of the sum of two exponentials, both with the same exponential parameter, exponential rate. An Erlang 100 will give me the sum of 100 exponentials. So an Erlang is just the sum of exponentials, and the k is how many exponentials are being summed. That's the reason why if you look at the probability density function for an Erlang, so here, as k gets large, so down here, this blue one is with a k of 9. This is the largest k here. The distribution starts to look more and more like a bell curve. So it should not be a surprise by the central limit theorem. As k goes to infinity, an Erlang goes to a normal distribution by the central limit theorem, because it's a sum of independent processes. All right, now another way that I can mess with an exponential is by introducing a shape parameter, and that is what you do with the Weibull distribution. So Weibull distribution is they took an exponential CDF, like you can see over here, and instead of doing x divided by mu, or x lambda, which you would do in a normal exponential, they added, it's a little bit of a heuristic, they raised that thing to a shape parameter k. When k is equal to 1, this CDF is the exponential CDF. But as k gets larger or smaller, it shapes the probability density of the resulting distribution, pulling it away from the exponential in either one way or another. It kind of either turns it into a ski slope here, or it starts to make it more humped. And this is a distribution you use when you have a process which is exponential-like in some parts of the outcome space, but otherwise needs to be shaped in a way to become more realistic in other parts. And so if you know something that tends to be exponential-like, but it fails more often early than late. So these are things that like need a burn-in process in order for to weed out the bad ones. If you know something that is it's likely to fail within the first 5 minutes of its life, but then if it manages to survive the first 5 minutes of life, it'll last 5 years. Then maybe this Weibull distribution pulled into this shape is what you want, where you've got most of the failures happen early. And then if you again, you can weed those parts out through a burn-in process, and then you've got the rest out there. If it's the other way around, where you know that this product never fails early, but then suddenly at like a year, they all die. It's kind of like a light bulb or something like that, where they hardly fail right out of the box, but right when 2 years comes with a certain light bulb, or 6 months with an incandescent, it's plus or minus a couple of weeks and it's dead. Well, then you can take that k value and you can shape it the other direction, and then you end up getting this failure distribution. So when you have data that looks almost like an exponential, but it just needs to be reshaped, you can use a Weibull distribution. Reliability engineers love Weibull distributions, and that's because they give them a lot of flexibility. All right, and I think I'm going to hold off because we're at 11:44 on the discrete ones here. We'll cover those next time, but you get kind of a flavor of what we're going. So let me just hop to a attendance question, which, I guess I've peppered all the way to the end here. All right. So I'll put the attendance link back in the chat. And so the question I have here is, what is a good distribution to use when you have non-negative outcomes with a known mean? So looking for a good distribution when the only thing the stakeholders told you is that the outcomes have to be non-negative, and on average, it's 5 minutes or whatever. That's all I've got for you. So if you have any questions, happy to take them. Otherwise, we will see you in a couple of days. Any questions online? All right, so in that case, I will probably close up shop here online. If you have any other questions, feel free to post them, send me a note, or post them on the meeting pulse, and see you Thursday.